Uh, Hello, everyone. I hope you can all hear us. Let's see if we can share the screen. Okay, we are very excited today to tell you more about exploring neural networks for satellite image classification using Tensorflow and Google Earth Engine. Thanks for inviting us for this virtual meetup. Because we have many exciting things to show you today, but before that, I will give you a short introduction from the project we are working on. So Nyein and I, we are both working for the SERVIR-Mekong Project, and the SERVIR-Mekong Project is a unique partnership between USAID and the US National Aeronautics and Space Agency, also known as NASA. And through that partnership, we are harnessing space technology and open data to help address development challenges. So basically NASA realized that they're having a lot of satellite data, a lot of important information, which is not really used by especially many developing countries, for example, for disaster preparedness, disaster response, environmental management, etc. So they decided to team up with USAID, and they established different hubs around the world. So we have 2 hubs in Africa, 2 in Asia, and 1 in South America. And through these hubs, we work with government agencies in the different countries and teach them how they can use space technology for different development challenges. So we are working specifically in Cambodia, Laos, Myanmar, Thailand, and Vietnam. And actually today we are at the Ministry of Environment in Cambodia. So this week we are working with them on their land cover classification system. So in the SERVIR-Mekong project, we developed a regional land cover monitoring system. There is a link included in the slides. When you click the link, you can find all our land cover products, which we derive from Landsat imagery. We have a land cover product for every year from 1988 till 2018. 2019 is coming soon. And we created those products from Landsat, so we have a 30 by 30 meter spatial resolution for the 5 countries. And we used Landsat 5, Landsat 7, and Landsat 8 for developing these products. So during the last Earth Engine Summit, we saw that Google did a lot of work on implementing those new AI algorithms, which can be specifically useful for land cover classification. So for the last couple of months, we have been working on testing those different AI algorithms. And I'm very happy that our intern who started working with us around 6 months ago, that he is really taking this job on, and he has been testing and running many of those algorithms. So from here on, I like to hand it over to Nyein. Maybe Nyein, you can give a short introduction about yourself and then show us some of the work that you did.
Yes, hi everyone. Nice to meet you. And my name is Nyein. I studied my master's degree of computer science in Waseda University of Tokyo, Japan. And then now I'm currently working as a consultant in SERVIR-Mekong Project. Today we would like to present about how to perform land cover mapping using TensorFlow in Google Earth Engine. And then this is the overview of our proposed system. And then I want to explain how this system is created. So for the first step, we use satellite image. Mostly we use Landsat 5, Landsat 7, and Landsat 8, and then sometimes we use Sentinel-2 image. And for the second step, we collect reference data from OSM or from sometimes from collect ad for reference data or crop land, forest, water, and then other land type. After collecting satellite imageries and reference data, we sample our data set to train for TensorFlow. And then when we sampling our data set, we split our data to training data and testing data. And then in the later step, we will be perform data to validation. So after sampling training data, we train that our data in our Nyein network in TensorFlow. And then we exported that model in Google Cloud Storage. And then we create inference from Google Ad Engine. So I will explain the detailed step in the next slide. So this is how we create, how we collect reference data and how we create our label. Now, today we will present land for urban and water mapping using DNN and Unet model. So we collect our reference data from OSM data, and then some are from our SERVIR-Mekong reference data. And then we combine that data to create our label. So when we create label, we created 21% for square rectangle and then 85% to creating polygon. So after creating our reference data, I want to explain how we create cloud-free composite to use in our classification. For Landsat image, everyone know Landsat has 30-meter resolution, so it has many cloud and then shadow and then other noise. So we perform pre-processing of including 5 steps for pre-processing step. First, we filter image collection with date and region boundary in Google Ad Engine. And then after that, we perform shadow masking module. And then we also create cloud masking module. And then after finish cloud masking, we perform bidirectional reflectance distribution function, BRDF correction. And then we perform topographic correction. So after executing all of the 5 pre-processing steps, we got that SERVIR-Mekong Composite. We created our composite for Mekong River Basin. It includes Myanmar, Laos, Cambodia, Vietnam, Philippines, and Cambodia. We created our composite from 2000 to 2019, and then we combine our sample data to create our TensorFlow record. So for the next step, when we create our training data, we added covariate. Sometimes in computer science we call features in our data set to perform classification better than using. When we use less feature, the classification accuracy is lower. So in here, we added some covariate called spectral index, and to increase our classification accuracy. So we added band from Landsat, and then we calculated enhanced vegetation index, index-based beta index, and then normalize different index from different band, and then ratio index, and then SAVI index, and then we combine all of that covariate to our feature. So in one next step, we want to discuss how we perform normalization. for surface reflectance, we normalize our data between from 0 as minimum to 1 as maximum. And then for EVI, we use minus 0.1 to 0.9 for normalization. And then for NDVI, normalize different vegetation index, we normalize between minus 0.1 to 0.9. And then for SAVI, we normalize between minus 0.2 to 0.9. And then NBLI. NBLI is normalized parent index. We perform urban classification, so we consider that NBLI and IBI index fit best index in our feature. And we normalize between minus 1 to 0.25 and IBI for minus 0.6 to 0.2. So for the next step, we perform sampling. When we sample our data set, we split our data set into 2 data sets, 80% for training data set and 20% for testing data set. Currently in our experiment, we haven't yet created for validation data set, but in the later future process, we will create that one. So when we sample our data set, we can sample with different image patches. And then for DNN, you can also create only point data, and then you train for that point data. But for Unet, Unet is used for image segmentation. So if you want to use for Unet, you have to create your data set, sample data with image patches. So now we created 60 into 60, 32 into 32, and 64 into 64 different patches for different data sets. And then we tested our data. But one problem is when we created our sampling data in Google Ad Engine with the batch size or 128 or 256, Google Ad Engine computation error occur, and then we can create for that larger size. So now we just create 64 as the biggest one. So this is the detailed step of how we will train TensorFlow model for land cover mapping using Google Ad Engine. So for the first step in this figure, this was performed in Google Cloud. First, after we creating our sample and then our sample in Google Ad Engine, we export that our sample data to Google Cloud Storage as a TensorFlow record. And then we import that TensorFlow record from Python Colab, or you can use Python Colab or maybe other Python tools like Spider or Genius or something. Everywhere you can do. And then you have to prepare your data in the right format. If you want to train for DNN, your data set will be point or image patch, it is okay. But for Unet or other convolution data, your data set may be will have to be image patch, not point data. So after creating data in right format, we build our model. Our model using TensorFlow Keras. After creating our model, we validate our model, how is the accuracy and how is the result. And then we save that model in our cloud backend. And then we have to call that model from our Google Ad Engine, and then make that model as EE readable, and then push that model to AI platform. So in this script implementation, you can see how to import the training data. You can pull your data from the cloud or from your hard disk and directly train in TensorFlow. Now we call our data from our Google Cloud Storage with this train bed with Google Google storage, and then this two is our training data set. And then we create that data set as a TensorFlow record file in the cloud storage. So after importing TensorFlow record from the cloud storage, we have to pass that data in the right format to train in our model. So this script is for the passing all data in the right format. You have to pass your data in TensorFlow record, and then when you pass your data, you have to assign your feature. And then I will discuss feature selection in the next step. So this is the feature we use in our training. We use NBLI EVI that many covariate as I told in the above slide. And then we train using that feature in our model. And the one we found is when we train our feature in TensorFlow with CPU, and it is fine if you put your feature in this order, and then you can call from EE with this order or not. Maybe you put EVI first and then as IVI something, it will work. But one problem is when you train your TensorFlow model with GPU, not CPU, and then you input your feature with this order, with NBLI EVI as AVI, and then when you call that model from Google Ad Engine, and then you didn't write this, you didn't write the order the same, the output is really terrible. So in here, we sorted our band. We input this band order, but when we train that band in TensorFlow, order is changing. So we print that band order, and then we have to use that band order when we train in Google Ad Engine. So for the next step, I will discuss how DNN model will work with, there are many hidden layers. In our classification, we use 3 hidden layers. This is the neural network architecture of deep neural net with 3 hidden layers. This is input layer, and then this 3 layer is hidden layer, and then this is output layer. And this weight is weight value from the input, and then all of mathematical calculation is performed in this hidden layer, and then we got output with the weight value. And then in here, you can add many hidden layers, maybe 4 or 5 or 6, based on your data set and depend on what type of classification you want to perform. So we created our DNN model with 3 hidden layers. We create TensorFlow Keras model, sequential model. And then in here, we use 2 convolution to the layer. And then for every step, we drop out 50%. In here, we drop out 50%. We use drop out to solve over 15 problem in here. So it depends on your data. You can drop out 50% or 20% or 30% based on your data. Based on your data set, you can change that value. And then in this example, we perform multi-class classification. So in the activation function, for hidden layer, we use ReLU called redefined linear unit. And then for the output layer, we use softmax activation function. In here, for multi-class, we can use softmax and sigmoid for activation function. And then you can also use other activation function in TensorFlow, or there are many built-in TensorFlow activation function. But we use softmax in here because softmax can convert vector value to vector or categorical probability. So we want multi-class classification. So we use softmax in here. So in the next step, for regression, we use activation function as linear. In this step, we want to classify for water, this one is water or non-water. So our output is between 0 to 1, and it is regression problem. So we use activation function is as linear. So after I finish DNN, I want to explain about Unet. This is Unet architecture. Unet is implemented to perform image segmentation, especially for medical image. And its architecture is somewhat like that U shape. And then in here, it is input type, and then this is output segmentation map. And then in the Unet, there are convolution layer, and then maximum pooling layer, and then app convolution layer, and then concatenating layer. So this is the accurate image, and then we encode, sometimes called downsampling, our image to, in this example, they use 572 as their image size, and then they encoded to 284, and then 140 and 68. And then they perform maximum pooling. And then they, after finish encoding, they perform decoding called upsampling. And then as a result, we got output segmentation map as the same. If we use 64 into 64 side, our output will be 64 into 64. If we use 256, our output is 256 image batches. So this is the Python script or Unet implementation using TensorFlow. So in here, first one is convolution. We separated 3 parts. First one is convolution block, and then the second one is encoder block, and that one is decoder block. As I have like this in this figure. First, we have to encode our image. If our image is 64, we encoded it and then in here, this padding equation means our input is 64, and then our output will be 64. If you put padding as origin, the output image size will be different. So this is the detailed implementation step of Unet. And then for activation, we use sigmoid. Yes, and then I want to discuss about hyperparameter tuning in our model. We perform our classification using many hyperparameter tuning technique, and then test that for our data set. For urban image classification, we added pan-Japanese image, pan, and OSM data for hyperparameter tuning approach. And then we also tested with different activation function, sigmoid, softmax, linear, and ReLU. And then for optimizer, we use SGD, ADAM, and then IMSPROP. And then for the loss function, we use binary cross entropy, categorical cross entropy, mean square error, and sparse categorical cross entropy. So, for binary cross entropy is used for regression, and then categorical cross entropy is used for multi-class classification. And then mean square error and sparse categorical cross entropy can be used for both. And then for the accuracy as a metric, we calculate with using root mean square error and mean absolute error, and then also overall accuracy value. And then we also try with different approach and different learning rate. So after training our model, we perform accuracy assessment. As but I have already do, we separate 80% and 20% for testing. So we test our 20% data set, and then we evaluate our testing data set in accuracy assessment. So after performing all of the steps, we exported our AI model to Google Cloud, and then we create our inference from Google Ad Engine. This is the Google Ad Engine code, how we call our TensorFlow model from Google Ad Engine. We call our TensorFlow model with ee.model from AI platform. And then you have to give your project name, model name, and version. And then we created our inference, urban and water. And in here, we found one of issue. When we input our time size with 32 into 32 and 60 into 16, it works. But when you put our input time size with 64 into 64 and 32 or 32 something, it causes error, it shows error, large input time size problem in Google Ad Engine. And then this problem occurs because of that equation. In this equation, you can see our input time size and then 2 into input over left side dot modulus 16 should less than 256 megabyte time size. If it was over that scale, it will cause error in Google Ad Engine based on Google Ad Engine computationist power. So for the last step, we call our model in here, and then we created inference from our neural network model. And then this is output of DNN for urban primitive in Jakarta, Indonesia. For this one, mostly we use for OSM data. And this is the result of urban primitive in Jakarta. The next one is output or Unet. In here, we use Unet, FCNN for urban primitive in Bangkok, Thailand. For Bangkok, most of our training data are from our SERVIR-Mekong reference data, and then we combine some of OSM data and then also with Pan-Japan data, and then we got that result. This one is water Unet model for Laos. And then for that data, for that one, we use our SERVIR-Mekong reference data, and then we got water model. So I want to discuss advantages and disadvantages of neural network over traditional machine learning algorithm. At first, for advantages, neural network is flexible, and then it can be used for both regression and classification problem. And then neural network can work for any data that can be made numeric because it was executed based on mathematical model with approximation function. And then for when we train our neural network with big data set, we got high accuracy with best accuracy. And then we can be trained with any number or input or layer. So we can adjust based on our data and then our output, how many input layer we can add or something. So these are the advantages on Nyein network. For traditional machine learning process like random forest and CAT in Google Ad Engine, we can train with many other input and layer, and then we can also perform hyper-tuning approach. But Nyein network has some disadvantages. It is computationally very expensive and time-consuming to train with using only traditional CPU. And then Nyein network depend on the training data, so it can lead to overfitting and generalization problem. So when we train our data, when we train data set with many overfitting problem, we have to make hyper-tuning. So for the validation and future work, we were focused for validation process using TensorFlow in the next process. And then we will define specific problem statement of our model. And then we will specify how to improve. We can improve our model by improving model performance with our data and then feature tuning. And then maybe with that network architecture or algorithm. And then we can also improve performance with ensemble. And then we will focus on that work in our future process. This is the link to our work.
Thank you, Nyein. That was the end of our presentation. So I'd like to hand it back to you, Sabrina.